This video lecture is for BSc 3rd semester Physics of Mysore University. Dear students, in this session I will discuss about series LCR circuit, derivation of current when AC is applied to a series LCR circuit by assuming exponential solution, and discussion of correspondence between series LCR circuit and damped driven oscillator. Before going to our discussion, let us recap what we have learnt in the previous class. We have learnt about the construction of an AC circuit consisting resistance and capacitance, that is the RC circuit. Next, expression for current when AC is applied to RC circuit, and also impedance calculation and its variation with frequency. For this session, these are the prerequisites: knowledge about response of AC circuit with series inductance, capacitance and resistance; knowledge about impedance in an AC circuit; knowledge about variation of current in an AC circuit. Now we shall discuss about series LCR circuit and the derivation of current when AC is applied to series LCR circuit. A series LCR circuit is nothing but an AC circuit consisting of a resistor, capacitor and the inductor in series. Here you can see in the picture there is a AC voltage applied to the series LCR circuit. The applied voltage can be given by V is equal to V0 into e to the power j omega t. According to the Kirchhoff's voltage law, the applied voltage V can be the sum of the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor. Hence we can rewrite this equation as V0 into e to the power j omega t is equal to Ri plus j omega Li plus 1 by j omega c into I. We will write the expression for current I is equal to V0 into e to the power j omega t divided by R plus j omega L plus 1 by j omega c. That will become I is equal to V0 into e to the power j omega t divided by R plus j into omega L minus 1 by omega c. For simplification, we shall substitute the value for R as R is equal to Z cos phi, and omega L minus 1 by omega c, this term is replaced by Z sin phi, where Z is the impedance of the circuit and phi is the phase angle between applied voltage and the corresponding current. After simplification, we get the expression for the current as I is equal to I0 into e to the power j omega t minus phi, where I0 is the peak current in the circuit that can be given by V0 by Z. Thus, when a complex voltage of V is equal to V0 into e to the power j omega t is applied to LCR circuit in series, the current lags behind the voltage with a phase angle of phi. So here Impedance Z in the circuit is the ratio of effective voltage to the effective current. The impedance also depends upon the angular frequency. Here the current amplitude also depends on the angular frequency. The circuit has complex impedance whose real part is equal to resistance R and imaginary part is the resultant of inductive reactance and capacitive reactance. Thus the impedance is equal to square root of R square plus omega L minus 1 by omega C whole square. Next we shall discuss about the correspondence between series LCR circuit and damped driven oscillator. We know that an LC circuit behaves as a harmonic oscillator. This is similar to a mass and spring simple harmonic oscillator with no friction. In an LC oscillator, the charge and the current in an LC circuit oscillate. It is known that both capacitor and inductors store energy in their electric and magnetic fields respectively. A circuit containing both an inductor and a capacitor can oscillate by shifting the energy stored in the circuit between electric and magnetic fields. The resonant frequency of an LC circuit can be given by omega is equal to 1 by root LC. The oscillations will be gradually attenuated if we introduce a resistance to the circuit. It is similar to a mechanical system oscillations which are damped by introduction of a friction force. An LCR circuit behaves like a damped harmonic oscillator. Because an LCR circuit is a damped harmonically oscillating system where the voltage across the capacitor is the oscillating quantity. For the introduction of a small resistance R, charge on the capacitor and thereby the current in the circuit decreases exponentially. The circuit forms a harmonic oscillator for current and resonates in a similar way as an LC circuit, but by introducing the resistance increases the decay of these oscillations, which are also known as damping. Hence, an LCR circuit behaves in exactly similar way as a damped mechanical oscillator. Here, alpha is equal to R by 2L is called the damping coefficient. Hence, we can conclude that an LCR circuit behaves like a damped harmonic oscillator.